I am Theo, and this is the block slab problem. So here we have a block, it's 0.5 kilograms, and we have a slab it's on, which is 3 kilograms, and the block is moving at a certain initial velocity, which is 4 meters per second, and there's some friction between the slab and the block, and for this first part, we're just going to draw out the forces acting on each object. So first I'll do the block. Okay, here's the mass. So as always, there's gravity. In this case, there's also a normal force against the slab. And that normal force is countering out gravity. This is going in the positive y direction. Speaking of that, I'll define my axes. Okay, and then the last force on the block is the force of friction as it moves to the right, or in the positive x direction along the slab. So if it's moving in the positive x direction, the force of friction must go in the negative x direction. Alright, so those are all the forces acting on the block. So now the slab. Okay, the slab also has gravity. So in this case, the slab, there's again some normal force between the block and the slab. And so in this case, for the slab, that normal force is actually going to be pulling down because the block is pushing down on the slab. So let's see, I'll label this normal force NX. That represents the normal force between the block and the slab. So this is NX. And there's also some normal force pulling the slab upwards just from the ground. And I'll just call that N. That's what we usually label normal force. And then finally, the slab has some friction. So because it is being pulled to the right by the block, the friction is going to the right, or in the positive x direction. So boom. Those are our forces. Okay. So the next question defines VF as some velocity where at a given point the block and the slab both reach that velocity. And they're also telling us that it's before the block falls off the slab. So you don't have to worry about anything with the y. Okay, so in this case, I'm going to use conservation of momentum equations, which you might think wouldn't work because there's some energy lost due to friction. But in this case, the energy lost due to friction, well, the block is losing energy. That energy is actually turning into kinetic energy in the slab. And because in this conservation of momentum equation that I'm about to use, I'm going to consider the block and the slab to be part of one system. Within that system, no energy is being lost. That's why I'm able to use conservation of momentum. So here's the equation. Okay, so you might notice that there's no term for mass of the slab times its initial velocity. That's just because the mass of the slab starts out kind of standing still, so that velocity is 0. And then, yeah, the rest of it is pretty standard. m1v1 plus m2v2 equals m1v1 final plus m2v2 final. So yeah, in this case the final velocities are the same. So now we just need to use a little bit of algebra to solve for the VF. Okay, so yeah, I just took out the VF and then divided by those two variables. Let me grab my calculator, I'll plug in the numbers. Okay, so we got MB, that's 0.5, times V0 is 4, divided by the sum of the masses, so 0.5 plus 3, and that's going to give us 0.57, two significant figures, meters per second. I also could have done this without a calculator, just being like, let's see, that would, numerator would be 2, denominator would be 3.5, so that's equal to 4/7, but I kind of need a calculator to actually evaluate that fraction. Okay, so there we go. Okay, so in part C, they're asking us to calculate the distance that the slab has traveled by the time both objects have this velocity. Okay, so let's talk about the energy of the slab for a second. So at the beginning, I'm just going to talk about kinetic energy here, and that's because, well, A, there's no spring, and in terms of gravitational potential energy, the slab always stays at the same height on the y-axis, so that energy is going to be constant. I don't need to worry about it. It'll be the same on both sides. All right, so in terms of kinetic energy, the slab has 0 at the beginning, and then over time, energy lost, like energy that the block loses due to friction, is transferred to the slab. So it gains some energy due to friction, which I'll call WF. It stands for like work. And at the end, it has a certain amount of kinetic energy, or 1/2 mv squared. In this case, the V is VF. So okay, so there's our equation. And again, we're solving for a certain distance. So in this case, I know that the work due to friction is equal to the force due to friction times the distance. So if we can find force of friction, we kind of already know this because we know the mass and we solved for VF. But if I can find the force of friction, then we should be good to go. So let's talk about what this force of friction actually is. So we know that force of friction is equal to, I'll just write it like this, is equal to mu n. In this case, it's kinetic constant of friction because both objects are moving at this point. The force due to friction, when we talk about n, we're talking about the normal force between the two objects that have friction. So in this case, the two objects that have friction are B and S. The ground does not have friction. So that means we're talking about the normal force between B and S. And I labeled that NX, as you can see here. So just not to confuse things, I'm going to call this NX as well. Okay, great. So in order to find out what NX is, let's do a little bit of a work with these free body diagrams. So I'm going to look at the block, and I'm going to do a force mass acceleration equation to solve for n. So force is in the y direction. We have one positive force, which is nx, and one negative force, which is just the force due to gravity. And we know that both objects are not moving at all in the y direction, therefore they have no net acceleration in the y direction. So mass times acceleration is 0. So therefore, that's true. And that's pretty much it. So now we can plug that back in here. I'm going to save this, we'll need it later. And then, yeah, so work equals force times distance. So if we kind of plug that back in here, we can say distance is equal to 1/2 mass slab final velocity squared divided by the force, which is equal to mu k, mass of block, gravitational constant, and I'll just plug that into my calculator. Mass of the slab is 3 times 4/7 squared divided by 2. Divided by 2, there's 1/2 times 0.2 times 0.5. I'm using 9.81 for gravity. Okay, and I'm gonna get a number that rounds to 1/2 meter. Pretty round number, that's nice. Okay, great, so that's B and C. So the last part asks us to find the work done by friction on here. So actually we don't need to use any of this at this point. We already have an equation kind of from part C that will solve this. So we know that work due to friction is equal to 1/2 mass of the slab, final velocity squared. Again, we're talking about the work done by friction on the slab, so that's why it's mass of the slab. And I'll just plug that into my calculator. Yeah, it's already here. I'm just going to plug it in. Okay, and I get a number that rounds to, let's write it down, 1/2. That rounds to 0.49, and that's the unit of work, so it's the same units as energy, which is joules. So there we go. So just to summarize, we've got our free body diagrams there. We have our kind of like when the velocities are the same, that velocity is 0.57. We've got the point, or well, not exactly the point, but the distance at which that occurs from when the slab was at rest, which is 1/2 meter. And then we've got the work done by friction on the slab by the time it gets to that velocity, which is almost 1/2 joule. So yeah, thanks for watching.